Hi students, in this class we will study different methods to improve the power factor of an inductive load. We consider an induction motor. This water pumping system uses an induction motor. It's a transmission system through which the power is transmitted and delivered to the induction motor. Actually, for the operation of induction motor, we need to supply both active power and reactive power. What is active power? P is equal to VI cos phi. What is reactive power? It is VI sin phi. If you draw the currents triangle, this is your currents vector. This is your I cos phi term, and this is your I sin phi term. So one is I cos phi is your active component of the current, and I sin phi is the reactive component of the current. I cos phi will make active power and I sin phi will make the reactive power. Actually, both the components will be transmitted through the line. Both I cos phi and I sin phi components, both components will be transmitted through the line. It is transmitted over a long distance. While improving the power factor, we will supply this I sin phi component locally by some methods to the induction motor. Now, what is the component that is to be transmitted? Only I cos phi component, because I sin phi component or the reactive component of the current is supplied locally. Or I can say the reactive power is supplied locally, only the active power has to be transmitted. So active power is transmitted through the lines, transmission distribution lines, and the reactive power is supplied locally using some methods. So now the transmission line is relieved of certain currents. Now it need not to carry I sin phi component of the current. Now we'll see the methods to improve the power factor. In all the methods, we are giving the reactive power locally to the inductive load. The first method is static capacitors, the second method is synchronous condenser, and the third is phase advancers. Now consider the first method, static capacitor. We have an induction motor which is working at lagging power factor. We'll see how we can improve the power factor. So now we're going to connect the static capacitors. Now all the three phases will be connecting capacitors. This is in the second phase. And this is the capacitor connected in the third phase. Now capacitor currents will be flowing through this line. The induction motor draws some current Im. Now we'll see how the power factor is improved. Suppose this is our voltage. Is the currents drawn by the induction motor. You can mark this as Im. It lags behind the voltage by an angle 5 radians. Now we are going to connect the capacitor bank, so which will give a leading current. It's an ideal capacitor. So the capacitor current is IC. Now what is the resultant current? How will you find out the resultant of Im and IC? Draw the parallelogram. Now this is the resultant current. This is I, the resultant current, and here the phase angle is improved to a certain angle. You can say phi dash. Now the phase angle is reduced, or the phase angle is changed from phi to phi dash. So phase angle is reduced, or your cos phi is improved. The power factor is increased, but the power factor is improved. So initially we had Im. Now when the capacitor is connected, the total current is I, which lags behind the supply voltage by an angle phi dash. Now phi dash is less than phi, so cos phi is improved. Let's see the second method, synchronous condenser. You can assume a three-phase inductive load here. This can be an induction motor or any other inductive load. And this current is lagging in nature. Let it be IL. This is working at lagging power factor. Here instead of the capacitor bank, we use a synchronous condenser. It is a synchronous motor working at leading power factor. Synchronous motor has a speciality. It can work at any power factor. It can work at lagging power factor, or at leading power factor, or at unity power factor. By adjusting the field current of the synchronous motor, we can change the power factor. Now this synchronous condenser is working at leading power factor. This is working at leading power factor. We call it a synchronous condenser. Actually this is a synchronous motor working at leading power factor. Suppose this is our voltage. This is the load current. Now you have connected the synchronous condenser. Suppose this is the synchronous motor current. Let it be IM. Let this current be IM. What is the resultant of these two currents? You have to draw the parallelogram. Now this is the resultant current. Initially this was the power factor. This was our initial power factor. Let it be phi1. Now what is the power factor? The phase angle is reduced. This is phi2. Even here when you look at the sum of the two currents, IL and IM, this is your resultant current. The phase angle between the resultant current and V is reduced. So here the phase angle is reduced from phi1 to phi2, or you can say the power factor is improved. Let's see the third method. It's called a phase advancers. Actually this is a small AC generator or an AC exciter. In order to understand the use of phase advancer, let me tell you why this induction motor works at lagging power factor or a log power factor. Actually, a stator draws exciting current from the supply lines. Actually, this exciting current causes the lagging power factor in the induction motor. Now, this exciting current is supplied by another small AC generator or from another AC source. As the motor gets exciting current from another source, it need not to take the current from the supply lines. Now the supply lines is relieved of this lagging power factor current or the lagging current. Now this exciter will give lagging current. So the generator takes only the active component of the current from the supply lines, because the phase advancer is ready to supply that lagging current.